talks on sublinearly Morse boundaries.
Let's see. Yes, thanks a lot for enduring all this. I see the number of participants has gone down quite a bit throughout the days, but which is expected. So yeah, I mean, like today hopefully will be won't be so complicated of a talk, will be a light talk, but there's kind of like a new trick I want to show you, right? So we have this boundary now, which we like very much, I hope, the sublinearly Morse boundary, right? So the statement kind of we did yesterday was, I mean, I haven't finished it, but like Julia will finish it for me. But for the case of the magnitude class group and the relative hyperbolic groups, if you do a random walk with some finite support, then the generic direction with the random walk is going to be sublinearly Morse, right? So this follows basically from some known statements. So there's some underlying hyperbolic structure there, right? And then so you have some subsurfaces in the Rafi class group case, and then this peripheral subgroups in the relative hyperbolic case. And then the amount that you spend in each of those guys is sublinearly bounded, and that gives you sublinearly Morse kind of behavior. So today we want to talk about the Patterson-Sullivan measure at infinity. So I'm going to spend some time defining that, but this is kind of very different from the random walk situation, right? So the measures that you get from Patterson-Sullivan measures, like there are singles in random walks and so on. But so it's kind of like a completely perpendicular notion of generic, and yet the sublinear Morse directions happen to be generic, right? So if your group has some kind of a hyperbolicity in it, the idea is with any reasonable notion of genericity, the generic direction, generic going to infinity, is going to be, in fact, sublinearly Morse. So okay, so the setup is that the X D is a cat0 metric space. But I think everything I want to say also true for the type molar space. The type molar metric. So for people who know that, they can in the back of their head follow along. I may mention some things about it, but if you don't, you can just look at the cat0 thing. But I want it to be some kind of a hyperbolicity to be present here. Right? A cat0 space could be just R2, and R2 doesn't have any sublinearly Morse geodesic in it, so it has to be at least one thing in it. So but also in the group action, right? Okay, so let's say G acts on X geometrically. So geometrically means it acts by co-compactly and by isometries. Okay. And then X should have has at least one rank 1 geodesic. So what is a rank 1 geodesic? Is a geodesic in a cat0 space that bounds a flat. So this is the non-ranked 1 behavior. So if every geodesic bounds a flat, then there is no hyperbolicity here, right? Like if you look at balls here, they contract to the same, they project to something of the same size. There is no contraction of any kind. So if your space is like a product space or something like that, that's what happens, right? In fact, there are like conjectures which says that's the only thing that can happen. Like, so there are rank rigidity conjectures which say that if you don't have any, and this should be a very mild condition. Like you basically should be a product, or maybe some kind of a higher rank symmetric space or something. So there are statements like that, conjectures like that. So yeah, hopefully besides the cases that are like completely a product or like higher rank symmetric spaces, this should always hold. So this is our setup. And so let me pick a point, maybe X in here, right? So this is, and I'm going to give you like some definitions of the Patterson-Sullivan boundary. So I write this visual boundary to mean the visual boundaries. Kim kind of defined this and spent some time on it, so I don't have to do that. Is basically the space of geodesics going to infinity up to fellow travel and you know up to fellow traveling, which actually, if you don't, yeah, it never happened. So the geodesics rays cannot fellow travel in Kasra space, and then yeah, you put the metric like a T metric or some topology like that. We don't really so much care about topology in this talk anyway. Okay, so what is the Patterson-Sullivan measure on the visual boundary? Just one S, I think. So, I mean, you want to have a process. It's basically a counting process, right? So I'll give you like 2 or 3 different ways of saying the same thing. So one is like you pick a ball of radius R. Here's your point X. You pick all the orbits of X, G of X, right? That are inside of in here, inside of ball. So let me maybe give you this in notation. I would write gamma sub R of X, gamma G. I have G. My group usually should be gamma, but it's G now. Okay. So this be the set of points Gx, where G is in G, and the distance between X and G of X is less than or equal to R. Okay. So then I want to look at like a distribution of these guys and see what they converge to at infinity, right? So so one way to do that is like to put a delta measure on any of these guys and then take the limit, right? So I want to look at a measure mu x r to be the sum of delta measures at the points gx, where gx is in this g, what was my notation? Rx, right? But I should, of course, divide by the total number of elements in the grx to be a probability measure. Right? So yeah, you basically put a light on each of these points, but then you dim the lights by the total number of these guys, and then you let the R go to infinity, right? You let R go to infinity. So every light which is in the middle, so has some brightness. As the R goes to infinity, the dimming factor goes to infinity, so they disappear, right? So the support of the limit of this measure is this, is not in the interior. There's no point in the interior as a support. So the support is entirely on the boundary. So I can take if I limit of that, so like mu be the limit as R goes to infinity. Maybe I should write like that, so I know what limit means. So as R goes to infinity, these guys converge to something called mu x. Right. R goes to infinity, and by converging I mean in a weak star topology. And this measure is what I call the Patterson-Sullivan measure. So this mu x is called the Patterson-Sullivan measure. Well, I mean, Dennis's contribution is only in the 3-manifold case, but anyway, still it's kind of timely. Dennis Sullivan recently won the Abel Prize, so we can at least mention some of his work. All right. Okay, so how do we understand this measure? So let's just spend a little of time understanding. Any question about all the notations so far that I have written on the board? Okay, the setup is clear. Kasra space, rank 1 element. We have the visual boundary. we look at this measures and take the limits. Right. So yeah, one way you can think of this is the following, it's like a counting measure, right? So if I pick, for example, an open set, let's say E on the boundary, and I wonder what the Patterson-Sullivan measure of E is. So one thing you can think about is the following, like pick a cone going in this direction, right? So this is an open set, so that's okay. And then I can pick a ball of radius R, and I can see proportionally how many of those points are in this cone, right? So the other way of defining this is that if E is an open set, it's a visual boundary, right? I can look at the cone X of E, so I guess we know what that is, and I can say that this measure nu X of E is the limit as R goes to infinity of the number of elements in this GRX intersect cone of E divided by the number of elements in GRX. So proportionally, how many of the points that we got, all these orbit points, how many of them are in this particular direction is the measure of this particular open set. This is just the same exact sentence. I haven't even changed it in any way. So some people say differently. Instead of picking the cone around E, you can pick like a ball U around E, right? And then do the same thing, count proportionally. I can change this to the number of elements in GRX intersect U. Because the visual boundary is a boardification, right? So if I pick a point in here, I can pick like some open neighborhood point in here, or if I pick a U, I can pick an open neighborhood. So pick any open neighborhood that you want, doesn't matter which one, and take the number of these guys divided by that. And take the limit again. So proportionally, if I go to infinity, how many points are near here? These three things that I wrote down, they don't even look different, right? They're exactly say the same thing. Like that, I'm just defining the weak star topology here.
Sorry, so what's on the right-hand side? Like, what's the last limit? I understood the first limit, but not the second.
Again, limit as R goes to infinity of the intersection of this GRX, which is the orbits that are in the ball, intersect U, right? So U here is a open set in X union boundary X, and E is U intersect boundary X. So there's a boardification, you pick an open set in the boardification, right? Then you look at the intersection of it with the other guy, so that's your E, right? And I want to say the measure of E is how many points asymptotically are in U, like proportional to the total number of points.
But what's U? I mean, it can't be just any open set that intersects E in the boundary.
I think it can.
I mean, what if you take the whole interior?
Well, open set.
Something like that.
Open neighborhood of E, I mean. Yeah, open neighborhood.
Okay.
Yeah. Open. Yeah, you're right. E. And E is a subset. Yeah. Okay, so okay, so this is the Patterson-Sullivan measure, and then so what does this mean again? Like, I mean, the question is, how do you translate this kind of sentence into something about the geodesic? So I pick a point in here, which kind of, you know, you feel like proportionally there's enough points going in that direction. Well, why would this mean that this particular geodesic is Morse or sublinear Morse or anything like that? So I want to tell you like what goes on into proving things like that. And the good thing is, like, you know, it's mostly out of the box. Like the theory has been developed so much that there's a lot known about the Patterson-Sullivan measure. So what we are going to use today is the relationship between the Patterson-Sullivan measure and the geodesic flow on the space, right? So yeah, maybe I should say a little bit more, like some properties of the Patterson-Sullivan measure. So for every point x here, I define for you a new x, right? What if I picked a point y, which is separate? Would I get the same measure? Right? No, you wouldn't. Right? It's much easier to be closer to here, right, than to there. So, and if I pick some point, let's say C on the boundary, then the measure from x and y is not the same. But there's a precise reason for it. It's possible that the y is closer to C than x is, right? If you're closer, then if I get the balls are equally closer, so there's an equal amount of weight associated to this point. So the difference of the new x and new y at this point is exactly related to the Boseman function of these two guys, right? So I hope everybody knows the Boseman function divided beta of cxy. This is basically you pick a point very close to that. You look at the distance to x and to y. So it's a distance between x z minus distance between y z, right? And you take the limit as z converges c. And then if I take the rod of negative derivative c, this is exactly equal to e to the negative delta times the Boseman function from point of view c as xy. For some delta which depends on the action of g on x. So some conformal density of the action delta. So yeah, there's a nice formula for this. Did I do this correctly? I hope I did. Yeah. So anyway, there's basically a family of measures for every point. So the basic idea is if I move this points by action of g, then the measure also changes by the action. So very nicely. So my goal is to we can use the Patterson-Sullivan measure to construct a measure on what I want to say is a unit tangent bundle. So let me tell you what that is for the cat zero space in a second. So I call it Sx. It is invariant under the geodesic flow. Okay, so let's see what the words in this sentence mean a little bit. If you have a manifold, you know what the unit tangent bundle is. If you have a cat zero space, you kind of don't, right? There's all kinds of branchings and so on. So what is a good replacement for a unit tangent bundle? So I want to, like, if I have a geodesic, I can go to infinity forward and I can go to infinity backward. That's what a unit geodesic does for me, right? A tangent space at a point. So instead of doing that, I just pick this exact thing and I say that's the point in here, right? So this is the space of parametrized geodesics. Right? So if you have a gamma, which is from negative infinity into x, and it's parameterized by arc length. Which is an isometric embedding of the ray into here, right? So I can see where 0 goes and think of this as where I am. And this geodesic is basically a direction in your space, right? So it tells you where to go. And then I have a geodesic flow. So GT is the geodesic flow. It flows from this SX to itself. And what it does is just, if you're here, then GT just changes the parameterization to be over there. So GT of gamma of S should be gamma of either T minus S or T plus S. Let's check it. So at time 0, I should be at gamma T, so it should be T plus S. Okay, so this is basically the unit tangent space, and I have a geodesic flow in it, which is just go forward along the geodesics. You can make this into a topological space. In case this is a manifold, it just becomes an actual sphere bundle over your manifold, right? But again, we mostly care about measure theoretic properties. So we don't care so much, but all we need to know is that if I have a element of Sx and I have a nearby element of Sx, then these two guys kind of fellow travel for a long time, right? So the topology is the way you think it is. Somehow I have a picture of Chris pinned on my picture. Maybe I should pin myself as being a narcissistic. All right, so. Any questions? I'm not.
So GT so S of X is the collection of all lines in
all parameterized
lines. So G of T as a set-wise just the identity map. It seems like if I understand.
No, I mean it changes the parameterization. Right.
Oh, I see. Okay, so you want to collect? Yeah, I see. Okay.
0 tells you where you are, right? So if I move forward, I'm a geodesic now. I'm somewhere else. Yeah. It doesn't act by identity, no. Yeah, topologically things change. I mean, somebody who is kind of like this line, maybe at the moment is kind of close to that, but if I flow forward, then they become really far away. Right? I mean, you think of this parameterized line is very close to this parameterized line, right? Because your center of attention is here. But if you flow both of them, then this parameterized line and this parameterized line are not the same at all, even though it's kind of the same line, but your point of view has changed. So you're completely somewhere else. Okay. Very good. So the other thing is that since G acts on X, G also acts on Sx, right? Kind of in a natural way. Like you send geodesics to geodesics, and the parameterization is also fine. And so this Sx divided by G is compact. So is a proper cat0, I don't know if we say proper, but cat0 space. And the action was geometric, was co-compact. So at each direction, you have the space of direction at each point is kind of compact. So this is going to be very compact. And then we have a geodesic flow here also, right? So GT is in fact defined on this Sx divided by G. Right. So, yeah.
Just to check. So SX contains every parameterization. So for each geodesic, there's uncountably many elements of SX.
Parameterization by arc length.
Yeah, okay. So for each geodesic, I see infinitely many copies, one for each base points.
One for each, exactly, one for each base.
Okay.
No crazy parameterization, just like move the, yeah, so exactly. I mean, it's kind of like the usual manifold situation, right? You have a vector defines for you a geodesic. You can go forward, and then the vector that you get by going forward, it still defines the same geodesic. Just where you are is different, right? Like there is usually, this is also true, that if you have a unit tangent bundle of a manifold, it's foliated by geodesics, right? So this is
Thanks.
Yes, one more question. I think I heard Abdul say something. No? No. Okay, very good. All right, so this is our space. So I would like to produce a measure, invariant measure on here. So a measure here of finite volume that is invariant under this flow, right? And the Patterson-Sullivan measure actually does that for me. So the Patterson-Sullivan measure on the visual boundary of X defines an ergodic invariant measure on an SX over G. With finite volume. So yeah, in different settings, this is the theorems of different people. So usually this measure, I will tell you a little bit more about what this measure. This is usually called the Bowen and Margulis measure. So Margulis did this in his thesis for negatively curved manifolds. Some work was done by Sullivan. The relationship between the Patterson-Sullivan measure and this Bowen-Margulis measure is due to Sullivan. In the case of this cat-zero spaces, it's a theorem of Rick's. So what is Bowen-Margulis measure? I'll tell you, like, for fun. Usually, what you can do is you can like look at the closed geodesics in your manifold, right, and take the long run, and you put like kind of delta measure or some spread the measure around each geodesic, and you take longer and longer geodesics, and you take the limit of that, and it converges to some measure on the whole space, which is invariant energetic flow. What we do here is like a little bit different. So I use this formula that I wrote for you, that the change of measure comes from this Boson function. I can use that to define an invariant measure on the space. So I do the most obvious thing. So I pick an open set in, I mean, to define a measure in here, I define a measure in SX as pi1 invariant. That's all I have to do, right? Then I take the quotient. So what is an open set in here? Well, a point in here is a parameterized geodesic, let's say connecting eta to C or something. So I need to find the density function here, right? So you should pick like some, so what is a nearby, like what is the open set around here? You have to pick an open set around here, open set around here, right? And look at all the geodesics going from there, and maybe some open set in this direction or something, right? Where the endpoint is. So basically, locally, there's a product structure, right? On this field of geodesics. I can change my starting point, I can change my endpoint, or I can change length, right? And I have a measure on each one of them, and I define a measure, right? So, define M on SX is measured by the defined like that. So the density of M at any point here, which I write as eta Cx, right, is going to be the d of mu x. So I have a point x and I have a forward measure. So I have the Patterson-Sullivan measure in the forward direction. and I have the Paterson-Sullivan measure on the backward direction. And then I have a length going this direction. And this is defines a measure for me. So this is, I use this measure density and integrate it, and I define the measure on Sx. Yeah, let's kind of digest this picture a tiny bit. So basically what happens, if I move forward along this geodesic from X to a point Y, right? The Boson function from point of view of C of X and Y is exactly this distance, right? I'm getting closer to that. The Boson function on eta from X to Y is the negative of this distance. I'm getting farther away from that. The length doesn't change. The going across is the same, right? The measure nu X and nu Y, they are different by the e to the theta negative theta times the Boson function. I always get this plus and minuses. I don't know which one is X, which one is Y, but the ratio of the d nu X, d nu Y is e to the negative delta times the Boson function from C of X, Y. If I get the signs correct. Right? Which means if I go forward, the measure here expands exponentially by e to the distance. And the measure here contracts exponentially by e to the distance. The product doesn't change, so it's volume preserved. Right? So this is exactly the same thing happens in H2 also, right? So what is, if I pick a point over here, right, and a particular vector, there's the front and the back. If I look at this direction, which is kind of like the measure that you would get from here, it's kind of like tells you it comes from the length of that. So these guys kind of expanding, right? And these guys are kind of contracting. So in this direction, things are expanding, direction things are contracting. In the flow direction, not much happens. Your measure preserving. So it's a usual hyperbolic dynamic that you have three foliations. Right? So you have a E, U, ES, and E0, and things kind of contract in a stable direction. They expand in the unstable direction, and that happens in the forward. So if I pick like a little cube here and move it forward, then it becomes kind of long, skinny cube of the same thickness. So the thickness is the same, the height is increased, the width has shrunken, but the measure hasn't changed. So it's you have an invariant measure. Okay, so right, so the Paterson measure was this counting measure. Then by just doing basic countings and cat zero geometry, you can kind of prove this equations, right? But the Paterson changes like by the e to the delta times the Boson function, and this tells you that the measure you have is invariant under the geodesic flow. You could write the formula globally and then define measure everywhere else and so on. But like this is the key calculation that these two numbers cancel each other from the forward and backward direction, and I have an invariant measure. Okay, so that is essentially the proof of this theorem. There's one word left in it. Well, why is it finite? Okay, let's not worry about that. The space is compact and so on, so it should be finite. The only thing is that is ergodic. Right? So this comes from this rank 1 property. So I'm not going to prove or tell you how to prove the ergodicity, but I'll tell you what that means. So, okay, can I erase some more stuff? Okay, so M is a finite dt invariant. Actually, let me say invariant ergodic probability measure on Sx over G. So what does ergodic mean? Ergodic, let's not define it, but the basic idea is that the geodesics go all over the place, right? It's not the case that some geodesics spend time here, some geodesics spend time somewhere else. All geodesics kind of spread out the same way. If I pick a generic geodesic moving around, it spends equal amount of time everywhere, right? So one consequence of ergodicity is that if W is a open set in our tangent space, if I pick, right, so now I'm in the quotient, right? But let me not draw the quotient anyway. I pick a point X and I pick a random direction eta, and I look at the geodesic going from X in the direction of eta. So let G eta, geodesic is not, okay, maybe I should put gamma. I put the G as geodesic for gamma eta be the geodesic ray starting at X in the direction theta. So W is an open set. So I can think of this as a geodesic in SX quotient G also, for just like in a quotient, right? So I want to say in the quotient, this geodesic goes almost everywhere. So for almost for nu X almost every eta. Let's rewrite this up here. The following is true. So if I look at the set of times, right? So let's look at the sometime R. Look at the set of times in the interval 0R, right? Such that here's Sx, be the quotient map to X as X over G. What should I call the quotient map? Usually pi, but pi is going to be closer to projection later, so let's just call it pi. Pi of G eta gamma eta T is a W. So look at the amount of time that your geodesic spends on W. And divide this by T. The limit of this actually exists at is some fixed theta. So there exists a theta 0. Yeah. For every W, there exists a theta 0, which actually is equal to this measure of W. So maybe I should just call it that. Okay, so I'm sorry, but back and forth, the dry sense again. So for any open set W, and for almost every direction eta, if I pick the geodesic in the direction eta and flow it forward and look at the proportion of the time that it spends in a particular set W, the limit exists and is equal to the measure of W. Okay, so it spends a linear amount of time in here, and it's true for like, so that the point is, this is independent of eta. It's not like the limit exists and it's different from different guys. Like for everybody, you would get the same exact answer, right? And the limit actually exists. Okay, so this is very good. So that means I can force something to repeat over and over again, right? And that thing can be anything I want. Like any phenomenon that I want is going to happen infinitely often, and forget about that. It's going to happen with a definite frequency, right? And so what phenomenon am I interested in? I'm in the business of proving things are contracting or like Morse or something like that. So I pick, and what I have is I have a rank 1 geodesic. I do have a segment that is somehow contracting, right? So that's what I'm assuming. So I pick my favorite segment, which is very, very long. I pick the point in the middle of it, right? And then I pick W to be some open set around that, right? So the W is an open set near the middle of the contracting direction. So much so that anybody who starts in this W, the geodesic kind of fellow travels this particular guy for a long time, right? So I can choose my W so that if yeah, what are our points in here? It's a parameterized geodesic. We already have gamma, but it's okay. If gamma is in W, then the segment gamma of negative L, this one is 2L, so is gamma L is strongly contracting or contract, let's say strongly contracting segment with the contracting constant so if W is small enough, the contracting constants of the original segment and these nearby segments are not so different, right? So I fix this N and L and W once and for all, and L is really, really large, and N is some fixed number. So I pick like my favorite contracting piece that I know exists in my space, right? Now I know that the generic direction kind of passes through this W over and over and over again. And every time it passes, it kind of builds up some contracting property, right? Okay, so the picture is as follows, that you have this geodesic that you like, and then these segments of the contracting that's appear all over the place, so that the limit of the time you spend here, the actually exists and is some positive number. Okay, so my goal is to tell you how would this prove. Okay, so I mean, this part I think hopefully is like not so unfamiliar to people, like if they have seen anything like that. But even if it's not, like this is the outcome of all the shenanigans. You have this Parsons-Sullivan measure, right? If you don't know anything about it, but what you should know is the final outcome is that it has this property, that it's going to have a lot of contracting pieces in it, right? So much so that this limit actually exists and is a positive number. All right, so now comes the slightly clever trick. So why would this mean sublinearly contracting, right? So in particular, you might think, well, it's possible that there's a huge gap in here, and this goes to a ginormous flat, and then I have like some ball that doesn't contract at all, right? But no. So yes, I want to say that so this condition, which I write as star, actually implies something slightly stronger, which I call a frequently contracting. So I would say gamma is frequently contracting. So I want to like upgrade this kind of for free to something which resembles more like the sublinear type of behavior. So instead of proving something is sublinear, I want to say something is better than linear for any linear function. Okay? And these two sentences are kind of the same. So So, I mean, the thing is, there is no lowest linear function. Any linear function, you have a smaller linear function. If you're not sublinear, then you are linear, and I can beat you by some other linear, right? And I win. So that is the goal. So I want to, okay. So what does this mean? So that means for every theta, so there are some parameters here, which is this L and N, which I have fixed once and for all. Okay. So your Ln frequently contracting, if for every theta there exists an R0, such that for all R bigger than R0, if I look at the 0 to R subsegment of gamma, and I pick any subsegment of it of length theta R, then there's a subsegment of that, which I drew by red before, whose length is L and is N contracting. So I want to say that these guys, it cannot be a large gap, right? The amount of gap that you can have is at most linear, right? And in fact is at most linear for every linear function theta. So then any segment of length theta R contains L long and contracting so for every theta. That's the key point in here. For every theta. All right. So let's prove this implies that. There are two things left. How much time do I have? I have some time. So there are two sentences left to prove. One is that this kind of thing that you spend fixed proportion of time in W implies that you're frequently contracting. And the second thing is to prove that the frequently contracting implies you're sublinearly contracting. With my definition of sublinear contracting. Actually, I should say sublinearly weakly sublinear contracting to distinguish between Chris's, which is the original name for the topic. Okay. All right, so let's go. So what is my trick? So I want to say, imagine this doesn't happen for a particular delta, and then I want to get a contradiction, right? So this definition here. So assume not means what? So star. So our claim is that the star implies frequently contracting. So assume not. What does that mean? That means there exists a theta that this doesn't happen at all, right? Like for longer and longer R's, this doesn't happen, right? And there exists also a sequence of Rn that are going to infinity, right? Such that the segment, and there's a sequence of Tn's, which are less than Rn, such that the interval Tn plus theta R does not contain any contracting subsegment, right? So in particular, it means it does not pass through the lift of W, right? Because if the segment went to a W, then it would have some long segments of length L, but it doesn't. So we have kind of long segments like that. Okay, so very good. Yeah, this is always along gamma. So my gamma is kind of fixed. So let me define this function f gamma of t to be the proportion of the time that you actually don't do a spend W. So I want to like name this function something. I have written down, so let me just do it again. So this function whose limit exists, I want to call f gamma of t. So the funny thing that happens is I want to calculate, so this is Tn. So note that the Tn is less than R. So Tn plus epsilon times R is less than Tn plus theta times Tn. Okay. I've just estimated this by that. Okay, so we have this segment that nothing happens. You don't visit W. All right, and I want to calculate f of Tn divided by f of Tn plus theta Tn. So from here to here, I spend no time in W. So the amount of time I spend in W here on average, is an exact amount, is the same as here, right? But to define f, I have divided by 1/t. So this part on the numerator and denominator is the same, right? It just cancels out. All is left is this part. So right, this is both how much time I spend W from here to here, which is the same as how much time I spend W from here to here. So that cancels out. So this is exactly 1/Tn divided by 1/Tn plus theta Tn. And then the Tn cancels out over 1. So it's 1 plus theta. So it's not equal to 1. So the ratio of the function at these two different times is not equal to 1. But if the limit of something exists, right? If you have a function which has a limit, then eventually it's within any small epsilon distance of each other. So the ratio between them has to actually go to 1, right? So this is not possible. I have found a sequence of points going to infinity where the ratio of the two values is bigger than 1, some fixed amount. So that's the contradiction, which proves the claim. So that's the cool trick. Right? The fact that you spend is not just that you spend this much time in W, is that the limits of amount of time you spend in W is actually exists. So you really can't spend a lot of time not in W. That would make your function wobbly, the function being the proportional amount of time you spend in W. Right? The limit exists. So the function is not wobbly. Right? Therefore, you cannot have any linear segment that you don't visit W for any theta, which means for every theta, you have to be frequently contracting. So for every theta and any segment of length theta r, there has to be a contracting subset. Yeah, I don't know if this was fast or what. Okay. So we have this. Yeah, I mean, I'm almost done. You get me, everybody, I'm sure, can finish the talk by themselves. So let's review what happened. So we have the Patterson-Sullivan measure, which was defined by this counting, but we turned it into in the flow that was invented under the geodesic flow, right? A measure which was invented under the geodesic flow, and it was ergodic. The ergodicity means that any behavior happens all the time in a very particular way. Like the proportional time that it happens is actually exists, the limit exists of how much this is happening. And this means the gap for the amount of time that this is happening cannot possibly be linear, right? Which means every segment of length theta, I'll draw a picture again. For every r and every subsegment of length theta r, so t plus, every subsegment, it could be anywhere you want. You have to have a thick kind of contracting subsegment. So why does that prove sublinearly contracting? Well, assume you are not sublinearly contracting, right? So gamma, so I want to say this frequently contracting implies weak sublinearly contracting. Right? So why is that? Because assume not. That means there exists a particular epsilon, right? And the points xn such that and yn. So you have xn and yn whose distance is less than the thing over here. So this is the norm of xn. And the projection is kind of large compared with that. Okay, meaning that in particular there exists an epsilon. And now you choose your theta to be less than epsilon, right? So you find R0 and take this R be bigger than R0. So we wait until R is big enough that this kind of theta kicks in. Now I have my counterexample X and Y, and then you will say, oh, these guys have really large projection to each other. But if this is epsilon R bigger than theta R, it has to contain a subsegment which is contracting, right? So what I can do is, instead of projecting things into this line, I can project them to this line, right? So a segment by itself can also be contracting. And my n is much smaller than L. The length of this is L, but the contracting constant of this is n. So the projection of x to the segment is somewhere over here. And projection of y to the segment is somewhere over here, which means the distance between the projections of x and y to the segment is basically L. But that's not possible because it's an n contracting segment. They have to be n. But these guys are pretty far away. So if the projections, let's say x and y and so x gamma and y gamma are epsilon r apart, then the segment x gamma gamma contains an L long n contracting subsegment. So what should I call that? Let's call it ZW. So then projection of x, this ZW is Z, the projection of y to ZW is basically W, and the distance between Z and W is equal to L, which is much bigger than N. And that's okay. Right. So the cool thing is, again, so the opposite of sublinear is that it's linear. and you cannot be linear because there's a smaller linear function that can beat you, right? So therefore you're sublinear, and there's actually you can come up with some function that works for everybody. Okay, yeah, I'm a little bit early, but let me wrap it up. You can also prove the same thing for random walks. It's not exactly the same, but it's not so different also. It's a little bit harder. But again, if you have a particular, so let me write this as a theorem, and I didn't write the name, so it's quickly I didn't finish. So this is theorem with Yulan Ching, Ilya Gekman, which starts with G. Which says that if X is cat 0 or a type on the space, rank 1 element, or rank 1 geodesic is all you need. Then for almost every eta, and okay, mu X is the Patterson-Sullivan measure, or the stationary measure associated to a random walk, finitely supported random walk. Then mu X, well, mu almost every eta in the boundary, this gamma X eta is sublinearly Morse. So the generic direction, I mean, you have kind of a map from the sublinear Morse boundary to the visual boundary. It's not a very topologically good map, but there exists a map, and they cover the support of any reasonable measure you can have. So we talked about the Patterson-Sullivan measure, but it's also true for the random walk measures. And the proof is basically similar because so again, you have your long segment and you're doing some random walk, and then it's possible that you land here, and there's a positive probability that you follow this over and over again, exactly like that, and go away. So there's some event that produces a contracting segment, right, in your random walk, and this has positive probability. If it has positive probability, it happens all the time. In fact, the proportion that it happens has a limit, right? So then you prove some similar thing to this frequently contracting, and then which means for every linear guy, you have to be more contracting than the linear function, which means you have to be sublinearly contracting. Okay. Right? Yeah, so it's kind of more evidence that this notion is kind of a natural notion, because so that's what Abdul was saying, that the sublinear Morse is much bigger than the random walk, and it is true, right? It is true. So like this is a very different measure from the random walk measure, and it still is generic, and still they don't cover all of it, right? There are all kinds of sublinear in the Morse direction that are, yeah, they don't behave this way. Okay, anyway, I enjoyed this very much. I hope you guys had fun with me. The 4 lectures are over, you're done with me. So thank you very much. And thank you for organizers to organize this. This was really, really great, all the stuff. Thanks.
Great, thank you, Kasra. And we might not be entirely done with you yet, depending on how many questions people have.
Yes.
I have a question. So you spoke about the Patterson-Sullivan construction, and then the resulting measure on the whatever the sphere bundle and ergodicity of that measure. Don't you need some amount of hyperbolicity? I mean, if you look at
you do the existence of rank.
You just look at Euclidean space, that's cut 0, but you can't do any of that.
That's correct. No. The assumption that there exists a rank 1 element is also an assumption for
I
that
see.
Rayleigh tubing error. Yeah.
I
It's
see.
not what I just needed. I need it for the ergodicity also. I need it. Yeah.
Okay.
That's the Rick's theorem. Yeah. That's correct.
What's so hard about doing this? And what, I'm just curious, like, why Tech-Miller space and Cat0 spaces only?
Well, so like, what else do you have in mind? So a variable negative curvature or something? Yeah, you can
Like mapping class group itself, for example. I guess there is no good boundary notion, maybe.
You have to act on some object. Yeah. You have to have geodesic flow that is ergodic. Exactly. No, the parallel measure on the mapping class group with the word metric is a whole another story, right? You don't have a good notion of boundary. You can say, okay, maybe sublinear Morse is a good place to start, so we can do that. I mean, this is extremely good question. Like, what is the Patterson Sullivan measure on mapping class group? Is on this? Can you say anything about it?
The metric space needs to be uniquely ergodic.
This is a group, so there is no unique ergodicity. In fact, the thing will depend very badly probably on generating set. Again, Julia has thought about this problem. Like, it's not even clear the growth rate is exponential, right? So you don't even know if the limits of the number. I mean, like, the denominator already, you don't know how it grows. Forget about the numerators. But the situation is quite bad. There has been some recent results. It's like, if you pick a generating set and then increase it by some other generating set to make it bigger, then, you know, like, maybe you can choose a generating set by adding like huge number of, like, rank 1 elements of pseudo-Anosovs to your generating set, and then things kind of more manageable. So people have proven, I forgot the Choi, yeah, he proved that at least the pseudo-Anosovs are kind of likely, and then the opposite is exponentially decaying. So if it's not pseudo-Anosov. So I mean, like, maybe you can pick a particular generating set like that, and then say something about the Patterson Sullivan measure. But no, I mean, we are kind of far off, unfortunately. There's no geodesic flow on any nice space that is ergodic or not. So Teichmüller space, yes. If you act on Teichmüller space, then yeah, you have. I didn't talk about, you have quadratic differentials, you have foliations, you contract, you have everything. That's why.
Thank you.
If I'm not wrong, we don't know even for any generating set that
that's
the
correct.
growth rate of the mapping class group is purely exponential. Right? That would be the first. So that's required for the Patterson Sullivan.
That the growth rate of number of elements in the bodies are in mapping class group are purely exponential. That's already a lot of progress.
But this would be implied, I think, if you had a single contracting element in the mapping class group, like with respect to the word metric, like a single strongly contracting element. And this is
yes. Good luck with that. That's right.
I mean, these types of questions have been coming. These types of questions have been coming to my mind a lot recently because of Harry's theorem that, like, the mapping class group is quasi-symmetric to a Kasra cube complex, and it seems, I mean, the strongly contracting property is not invariant, of course, under that, but it seems like one might be. I don't know. I mean, it seems helpful, yes, to like seeing whether you get no, yeah.
No, the technology is like, it's there. You just need like some beginning point to get the machine going. But the beginning is what fails at the moment. Yeah.
Yeah, the problem is almost basically all the models that we have of these objects are QI models. So
right.
we don't have a model where we can understand this metric in a finer way, because up to quasi-isometry is too weak, so you cannot even estimate the growth of the number of elements or something like this. So that's somehow the limit of all this classical Mazur-Minsky machinery in some sense, I think.
There is a workshop on this problem or something, like in a week or so, right? In AIM. So I imagine this kind of problems will be discussed. Maybe there'll be a breakthrough. by the end of it. So check again with people who are going to. Yeah, so I should advertise that. That's going to be exciting.